Dear students, welcome to EPG Pathshala. Myself, Dr. Raj Kishore Sharma, working as an Associate Professor in Department of Chemistry, University of Delhi. Today we are going to discuss about the module Analysis of Brunner, Emmett and Taylor Theory under the paper of Surface Analytical Techniques 2. In the analysis part, we will talk about the classification of adsorption isotherms, which are made based on the literature study performed by Brunner, Deming and Taylor, which is known as BD-DT. There are 6 types of sorption isotherms which we will discuss in details. Then we will discuss about the adsorption hysteresis, its origin and classification of hysteresis loop recommended by IUPAC. Basically, there are 4 types of hysteresis loop, which we will discuss. We will discuss each loop one by one. So after this, we will conclude BET technique by interpreting the data. The topic we are going to cover today: classification of adsorption isotherm, adsorption hysteresis, origin of hysteresis, IUPAC classification of hysteresis, and conclusion and recommendations. Before interpreting the BET data, there are certain terms to be discussed. First of all, we will discuss about the classification of adsorption isotherms. In 1985, IUPAC gave the classification of adsorption isotherms on the basis of literature study performed by Brunner, Deming and Taylor, BD-DT. They described that there are 6 types of sorption isotherms: type 1, type 2, type 3, type 4, 5 and 6, type 6 adsorption isotherms. So type 1 isotherms. Type 1 isotherms are obtained when adsorption is limited to few molecular layers, such as in case of chemisorption, and as we can see from the graph, it is concave to P upon P naught axis. There is one more condition for this type of isotherm, that is, they are obtained only when P upon P naught is much less than 1 and C is much greater than 1. In case of exclusive microporous materials, type 1 isotherm level of below the relative pressure of 0.1 mm. If it does not, then sample may exhibit appreciable amount of mesopores with pore size close to microporous range. Also, type 1 graph is an explanation of Langmuir isotherm that is based on monolayer coverage. Type 2 isotherm. The type 2 isotherm is reversible isotherm, and also these are the characteristics of non-porous and microporous adsorbent. These are generally observed in case of non-porous or microporous adsorbent. In this graph, the knee of the isotherm is an indication of completion of monolayer coverage and initiation of multilayer adsorption. In type 2 isotherm, the adsorption and desorption branches coincides. The next is type 3 isotherm. The reversible type 3 is convex to P upon P naught axis. Since type 1 was concave to P upon P naught axis, but it can be seen from type 3 isotherm that it is convex to P upon P naught axis. It depicts the unrestricted multilayer coverage. Type 2 exhibits knee point, but type 3 isotherm does not exhibit any knee point. This curve arises when lateral interaction between adsorbate molecules is stronger than the interaction between adsorbate and adsorbent surface. Now about type 4 isotherm. Type 4 isotherm is exhibited by mesoporous materials. In mesoporous materials, adsorption proceeds via multilayer adsorption followed by capillary condensation. Here is a question like, what is capillary condensation? Capillary condensation occurs at P upon P naught much higher than 0.2 or equal to 0.2. So 0.2 or higher than this, and it is indicated by the hysteresis loop, which is characteristic feature of the type 4 isotherm. In capillary condensation, The remaining pore space after multilayer adsorption is filled with condensate separated from the gas phase of the meniscus. The initial portion of type 4 isotherm is ascribed to the monolayer multilayer adsorption, as in case of type 2 isotherm. There are reasons for the appearance of hysteresis. This is the difference in pressure of capillary condensation and capillary evaporation. In this isotherm, the limiting uptake is over a range of high P upon P naught. Next one is the type 5 isotherm. Type 5 isotherm is also associated with the pore condensation, and hysteresis is present just like in type 4 isotherm. The initial part of the isotherm is like that type 3 isotherm, which indicate weak interaction between adsorbate and adsorbent. Important point to note here is that type 5 isotherm is uncommon, but it is obtained with certain porous isotherm. Last type is type 6 isotherm. Type 6 isotherm depicts stepwise multilayer adsorption on a uniform non-porous surface. This isotherm observed particularly in case of spherically symmetrical non-polar adsorptive. The sharpness of these steps depends on the homogeneity of the system and the temperature. Step height of type 6 isotherm represents the monolayer capacity of the adsorptive layer. The classification of adsorption hysteresis. The slide shows 4 pictures of different classifications: H1, H2, H3 and H4. These classifications are based on the recommendations of International Union of Pure and Applied Chemistry. Before discussing the classification, we will have a look on from where did these hysteresis originated. The origin of hysteresis is ascribed by 2 factors. One is the thermodynamic factor and the other one is pore connectivity or the network effect. The thermodynamic stability is associated to the metastability of adsorption or desorption branches. Namely, the capillary condensation or evaporation may take place at different pressure as compared to the pressure of coexistence between the gas and liquid-like phase in the pores. The pore connectivity or the pore network also causes the loop. For example, if larger pores are accessible only through the narrow pores, then the larger pores cannot be freed at relative pressure, corresponding to the capillary evaporation. It is because the narrow pores are still not vacant from the condensed adsorbate. Now we will discuss each type of hysteresis loop. First one is the type 1 hysteresis. As we can see from the graph, the 2 branches are nearly vertical and closely parallel over considerable range of gas uptake. H1 is associated with the porous materials consisting of agglomerates or uniform spherical structures in a regular arrangement. H1 hysteresis is also observed in materials with cylindrical pore geometry and relatively high pore size uniformity. The type H2 hysteresis. In this type, as it is seen in the graph, the loop is triangular in shape with sharp desorption branch located at the relative pressure close to the lower pressure limit of adsorption-desorption hysteresis. H2 hysteresis is observed in materials having channel-like pores with non-uniform pore size distribution, usually inorganic oxide gels and porous glasses gives H2 type of hysteresis. The type 3 hysteresis. Type H3 hysteresis, the desorption branch consists of steep region as shown in the graph. It consists of steep region with the closure of the hysteresis loop. H3 hysteresis isotherm does not exhibit any limiting adsorption at height P upon P naught. This isotherm is observed in materials which have non-rigid aggregates of platelet-like particles forming slit-like pores. The last one is type H4 hysteresis. Type H4 loop features parallel and horizontal branches. It is associated with the narrow slit-like pores and it is observed in particles having internal voids of irregular shape. Basically, broad pore size distribution. Now we will talk about surface area from the BET plot. We can calculate specific surface area from the BET theory using BET equation. The equation as shown on the slide reads as 1 upon V into P upon P naught minus 1 is equal to 1 upon C Vm plus C minus 1 upon CVm into P upon P naught. A plot of 1 upon V into P upon P naught minus 1 versus P upon P naught yields a straight line usually in the range of 0.05 to 0.35 of P upon P naught. The slope S and the intercept I of a BET plot are respectively S is equal to C minus 1 upon CVm, I is equal to 1 upon CVm. On solving the equation, Vm is equal to 1 upon S plus 1 and C is equal to S upon I plus 1. The total surface area can be calculated from the equation S is equal to Vm into Na upon m into 22,400. Low surface area analysis. It is possible to measure absolute surface areas using highly accurate volumetric adsorption equipment as low as approximately 0.5 to 1 meter square with nitrogen as the adsorptive. In order to measure even lower surface areas, the number of molecules trapped in the void volume of the sample needs to be reduced. This can be achieved by applying krypton adsorption at liquid nitrogen temperature for the surface area analysis. Krypton at approximately 77 K is about 38.5 Kelvin below its triple point temperature. T is equal to 115.35 K and it sublimates at about 1.6 torr. The saturation pressure of the supercooled liquid krypton is 2.63 torr, that is, the number of molecules in the free space of the sample cell is significantly reduced to 1 upon 300th time compared to the condition of nitrogen adsorption at liquid nitrogen temperature. Is a case study of nickel oxide microsphere. There are two graphs given. The first is between the relative pressure P upon P naught and quantity absorbed. The other one is the pore size distribution. The left hand side graph shows adsorption and desorption branches of nickel oxide microspheres, whereas the pore size distribution suggests the sample has variable porosity starting from micropores to mesopores. This isotherm can be classified as type 4 isotherm according to IUPAC classification. This work was published recently in Journal of Materials Chemistry, year 2009. The narrow hysteresis loop at low pressure region is an indication of open porous structure. The presence of macropores is indicated by the hysteresis loop at high pressure region. BGH pore size distribution reveals the pressure of multimodal and hierarchically porous structure. Hierarchically porosity means macro pores within mesopores. Low pressure hysteresis. It's again a case study. Commonly, hysteresis phenomena take place at high relative pressure due to the presence of metastable states associated with the capillary condensation of the probe molecule on mesopores. However, a low pressure hysteresis phenomena have also been reported for the porous solids such as ordered mesoporous silicas, zeolites, and activated carbons, etc. The work was published in Journal Physical Chemistry C in 2012. Here, the graph shows nitrogen adsorption-desorption isotherms at 77 Kelvin on zeolite silicate 1, measured using different equilibrium times, that is 10 seconds and 60 seconds. You see, there are two hysteresis loops are seen. First at lower P upon P naught and the second in the range of higher P upon P naught. The sample silicate 1 has been analyzed using two different equilibrium times, that is 10 seconds and 100 seconds. Although both measurements were coincident over the whole pressure range. An amplification of the region connecting both hysteresis loops, the low and the high pressure region. For low equilibrium times, that is below 100 seconds, the adsorption and the desorption branches are not able to match each other, giving rise to an artificial medium pressure hysteresis. Large equilibrium times, that is above 100 seconds, prove that the low and high pressure hysteresis are real phenomena on silicate 1, whereas the artificial medium pressure hysteresis between these two regions disappear. Conclusion from the case study of low pressure hysteresis materials. One can conclude that deficient degassing treatment and or a low equilibrium time, that is lack of real equilibrium, can give rise to unreal hysteresis phenomena at low to medium relative pressures. Care must be taken while performing the adsorption isotherms in porous solids to ensure the cleanness of the sample and to avoid the lack of equilibrium. Either an increase in the equilibrium time or an increase in the temperature of the thermal treatment is mandatory to ensure a true isotherm and or a true hysteresis phenomena. The presence of an LPH loop should be taken as a hint of the probable non-real adsorption isotherm and the corresponding mistake in the characterization of the porous solid. Now, the characterization of pore characteristics of micro and mesoporous materials using different adsorptivities. Different gases are used as adsorptives, including nitrogen, argon, and carbon dioxide. This is depending on the nature of material that is adsorbent and the information we are looking for. Using nitrogen adsorption isotherms, information on size distribution in the micro, meso, and macro porosity range, approximately 0.5 to 200 nanometer, can be obtained. Barrett, Journer, and Helenda, which is popularly known as BJH, is a classical pore size model developed in 1951. This is most widely used for calculation of the pore size distribution over mesoporous and part of the macroporous range. Argon is used for determination of the micropore size distribution in zeolite at 87 Kelvin or 77 Kelvin. Because the presence of a quadrupolar moment in nitrogen can result in enhanced interaction with the heterogeneous surface of the zeolite framework, leading to a more difficult discrimination between zeolites of different pore sizes. Argon is used for correct measurement of smaller micropores as in nitrogen adsorption occurs at lower pressure, P upon P naught values, than argon. For mesopore size distribution, argon adsorption 77 Kelvin shows limited application since the coolant temperature is below the bulk triple point. As a consequence, pore condensation vanishes in case the pore diameter exceeds approximately 12 nanometer. In case of activated carbons, carbon dioxide is often preferred as an adsorptive, since these adsorption measurements are mostly performed at temperatures near ambient, which will enhance diffusion process in the highly microporous system compared to the low temperature used in nitrogen and argon adsorption. This is a drawback of carbon dioxide adsorption at ambient pressure. Most of the equipments predominantly operates in the pressure range of vacuum of 1 bar on using carbon dioxide adsorptive. Only a limited range of micropores can be measured unless high pressure CO2 adsorption is used. Now we will discuss about interpretation of an isotherm. Pore size calculations for determination mesopore size distribution can be performed on both the adsorption and desorption branch of the isotherm. In presence of mesopores, capillary condensation will occur during adsorption and is preceded by a metastable fluid state. This state is called cylindrical meniscus, while capillary evaporation during desorption occurs via a hemispherical meniscus, separating the vapor and the capillary condensed phase. This will result in hysteresis since pores of a specific size are filled at higher pressures and emptied at lower pressure. So they are filled at high pressure and emptied at a lower pressure. Purely mesoporous materials that contains non-intersecting mesopores of cylindrical geometry and similar size, nitrogen or N2 isotherm will be of type 4, accompanied by a type H1 hysteresis loop according to IUPAC classification. More random distribution of pores and an interconnected pore system often results in the hysteresis loop of type H2 or H3. Now, finally, to summarize, students, what we have learned today is there are six type of adsorption isotherms. The recommended adsorptive for the evaluation of both surface area and pore size distribution is nitrogen, but this is not applicable for the low surface area solids. It holds good only for high surface area solids. Type 1 is associated with microporous materials, and type 1 isotherm is obtained only when P upon P naught is much less than 1 or the concentration C is much higher than 1. Type 2 isotherms are characteristic of nanoporous, non-porous or microporous adsorbent, and Ni in the isotherm indicate the completion of the monolayer coverage and initiation of multilayer adsorption. Type 3 depicts the unrestricted multilayer coverage. Mesoporous materials exhibit type 4 isotherm. The recommended adsorptive in nitrogen, except for the low surface area solids. For low surface area solids, generally less than 5 meters square per gram, krypton or xenon is used. In mesoporous materials, adsorption proceeds via multilayer adsorption following by capillary condensation. Capillary condensation is indicated by the hysteresis loop, which is a characteristic feature of the type 4 isotherm. Type 5 isotherm is uncommon, but it is obtained under certain porous isotherms. Type 6 isotherm is observed particularly in spherically symmetrical or non-polar adsorptive. The origin of hysteresis is usually ascribed to the thermodynamic or network effects, or the combination of these two effects. The first step is the interpretation is to be identify the type of isotherm and hence the nature of adsorption process: monolayer, multilayer adsorption, capillary condensation, or micropore filling. The calculation of mesopore size distribution is effective only if the isotherm is of type 4. Neither type H2 or type H3 yields correct estimation of pore size distribution. If the isotherm is of type 1 and type 3, BET method is not recommended. Not at all recommended. On the other hand, if the isotherm is of type 2 and type 4, the BET is suggestive provided that the value of C is neither too low nor too high. If the value of C is found to be high, then the pressure of microporosity is assumed even if the isotherm is type 2 and type 4. According to the IUPAC recommendation, hysteresis loop are classified into 4 types. The H1 hysteresis are also observed in materials with cylindrical pore geometry and relatively high pore size uniformity. H2 type hysteresis is observed in materials having channel-like pores with non-uniform pore size distribution. H3 hysteresis isotherm does not exhibit any limiting adsorption at high P upon P naught and is observed in materials which have non-rigid aggregates of platelet-like particles forming slit-like pores. Type H4 is associated with the narrow slit-like pores and observed in particles having internal voids of irregular shape, basically broad pore size distribution. This is all in this module. Thank you so much.